If you haven't already, please print this handout. This unit is about gases. And one big idea when talking about gases is something called the kinetic molecular theory. So the word kinetic refers to motion. So the kinetic molecular theory refers to the motion of molecules or the motion of particles. And this theory describes a hypothetical gas. So what I mean by that is this is a simplified model of what we would expect gas particles to behave like. So this hypothetical gas is called an ideal gas. So ideal in the sense that it's perfectly behaved and it takes up hardly any space. The particles are not attracted to each other. So the picture is these gas particles moving around, bumping into each other, and not reacting with each other at all. And the amount of space they take up is negligible. So that's what an ideal gas is. It's just a hypothetical gas. It's not an actual gas, but it's a nice model to talk about how gases behave. So along with gas particles taking up hardly any space and not being attracted to each other, the big idea in kinetic molecular theory is that these particles are in constant random motion. So constant in the sense that these particles are always moving, random in the sense that particles can move left, right, up, down, any direction, every which way, and they're just zipping around in the whatever container they are. And when they hit each other or hit the sides of the container, they just bounce back. Speaking of motion, there are 3 types of motion that any particle can exhibit. There's translational motion, rotational motion, and vibrational motion. So translational motion is basically particles moving in a straight line. So if I have a particle in one spot, it can move to a new spot. Or if it's here, it can move in any direction. This is all just translational motion. When we talk about rotational motion, this is the spinning motion of the particle. So let's say I have this particle. The picture is kind of like the Earth rotating around its axis. So we've got this particle, which I have in red. The axis would just be this imaginary black line here, and it would be spinning around its axis. So the particle itself is just rotating around. And when we talk about vibrational motion, think about the bonds within a molecule. So there's a back and forth motion of the atoms within a molecule. So let's say this is my molecule. So I've got 2 atoms bonded together. Those atoms within the molecule, they can undergo vibration. So they can move back and forth along the bond. They can get closer to each other and farther away. So this atom within the molecule can move towards the other atom. It can move away from the atom. So the vibrating motion within the molecule would be what we're talking about when we refer to vibrational motion. And I just have a note at the bottom here. The type of motion that predominates in a given sample depends on the freedom of movement of the particles. This in turn depends on the strengths of the attractions between the particles. And to explain what I mean by that, let's take a look at different states of matter. So think about the differences between solids, liquids, and gases. If I put them in a container, how would they respond? Well, if I put a solid into a container, it's just going to be a chunk sitting in the bottom. If I put a liquid in a container, well, it's going to spread along the bottom of the container. It's going to change its shape to suit the container. And if I put a gas in a container, well, the gas is just going to fill the whole container. So we can use this idea of how the gas, liquid, and solid particles behave to describe the shape and volume, the attraction between the particles, and then we can determine what type of motion predominates. So if we take a look at solids, the solid does not take on the shape of the container. It has a fixed shape. Also, the solid does not fill the container, so its volume is fixed. A liquid takes the shape of the container, so it has a variable shape, but it doesn't fill the entire container, so it still has a fixed volume. Gases, on the other hand, well, when you put a gas in a container, it will take the shape of the container, whatever it is. Also, the particles will fill the entire container. So gases have a variable shape and a variable volume. So because solid particles stick together, we would say the attraction between those particles is strong. Same with liquids. The particles stick together, so the attraction between them is strong. Gas particles, though, they spread out through the entire container. They're not attracted to each other very much at all. So we would say gas particles have a very weak attraction between particles. Because solid particles are attracted to each other very strongly, they're not very free to move around. Whereas on the other side of the spectrum, there's a very weak attraction between gas particles. That means those particles are free to move as much as they can, or as much as they need to fill the container. So when you think about the type of motion, well, gas particles, since they're so free to move around, there's a lot of translational motion. In fact, most of the motion of gas particles is translational. Solids, on the other hand, they are not free to move. There's not going to be very much translational motion of these particles. They are mostly undergoing rotational motion. Liquids, kind of in between, but basically the idea is all particles undergo translational, rotational, and vibrational motion, but the state of matter changes what the predominant type of motion is. So gases are mostly translational motion. Let's flip the page. When we talk about gases, oftentimes we will refer to the pressure of the gas. So going forward in this unit, we are going to talk about the relationships between pressure, temperature, and volume of a gas. So it's good to spend some time talking about what pressure is so that we have a good understanding of it going forward. So an important idea is that gas pressure is a force caused by the continual bombardment of a surface by the gas particles. So whatever the surface is, this would be the surface of the container that the gas is in, or it could be the wall of the room that the gas is in, or it could be your window. Any surface has gas particles surrounding it. So let's just say we have some gas particles. So these gas particles are just floating around with lots of translational motion. So if the particle moves in a straight line, it's going to hit the surface. So there's an impact there, which causes a force. If another gas particle moves and hits the surface, that causes a force on the surface. If we have another particle hitting the surface, that causes another force. So all of these forces, all of these impacts of the gas particles on the surface, all of those impacts, all of those forces add up. And it's the total of those forces that we call pressure. So that's why we say gas pressure is a force caused by the bombardment of the surface by gas particles. So one common example is the pressure in a tire. So if you're driving a car, you need to maintain a certain air pressure in your tires, or else you're going to get a flat tire. So if you think about inside the tire, those air particles, so those gas particles inside the tire, are hitting the tire, the rubber. And that force of impact caused by all those gas particles hitting the rubber inside the tire is what causes the tire to expand. So you need to maintain a certain air pressure inside your tires to keep them inflated. So I talked about how pressure is just the sum of all of these forces, and there's a unit for that. So the unit for pressure, the main one that we use, is called the Pascal. So the Pascal is a unit of pressure, and its symbol is capital P, lowercase a. There's also a kilopascal, so it's a metric unit. Kilo means 1,000, so a kilopascal is 1,000 pascals, and its symbol is kPa. Now, these are the main units of pressure. In fact, these are the ones that most scientists use today. These are the standard units, but those aren't the only ones. So here I have a list for you of some different ways of measuring pressure. So you can measure pressure in atmospheres, millimeters of mercury, or torrs. They're all valid ways of measuring pressure. They all have different symbols, and here's how you can convert between them. Millimeters of mercury, if you've ever had your blood pressure taken, it's measured in millimeters of mercury. So normal blood pressure is 120/80. Well, those numbers are measured in millimeters of mercury. And I just want to spend some time talking about that, millimeters of mercury, when I refer to this device over here. So this device, this was the first way of measuring air pressure, and it's called a barometer. So if you've ever heard of a barometer, that's a device that measures air pressure, or atmospheric pressure, the pressure of the air particles in the room or outside, whatever. And the way it works is there's basically a dish full of mercury, with a tube attached to it. The air particles in the surroundings will cause pressure to push down on the mercury in the dish. As the mercury gets pushed down in the dish, well, it needs to go somewhere, so it's going to go up the tube. So as the pressure of the gas particles outside pushes that mercury up the tube, well, you can measure the distance that the mercury travels up the tube. And that distance was measured in millimeters, so that's where the unit millimeters of mercury comes from. It's how many millimeters did the mercury move up the tube, and that's a measure of air pressure. So that's the basic design of any barometer, and that's what's still in use today.